Right, then the last speaker for today is Dan Browne from UCL, and he will talk about continuous time quantum walks.
Thanks very much, Marcus. So I'd like to start by thanking the organizers for putting on such a fantastic workshop. I'm going to talk today about some joint work. So this work was led by Bobby Banks, who's here, who's a PhD student co-supervised by me and Paul Warburton. But you also see this cast of thousands here. So Bobby took this project while it was underway, and he turned it into an outreach project. And he engaged a group of A-level students, so that would be high school students here in East London, and taught them quantum computing, taught them quantum walks, and got them involved in the project. And they actually delivered a very wide range of numerical results, which were very useful for us. And they became authors of the paper. So it was a very nice, big collaboration, probably the biggest collaboration I've been involved in for quite some time. So we've given it this kind of funny title, Continuous Time Quantum Walks for Maxcott Are Hot. And amazingly, the journal accepted that as well. So that's the official title there. I guess Quantum are a bit more liberal about these things. Here's a sort of more boring title, maybe more sort of descriptive. So I'm going to tell you about some heuristics we can develop for a very, very simple family of continuous time quantum walks, and how we can derive them from some pretty simple ideas from geometry and physics, and they lead to some nice heuristics, which are nevertheless analytic and be exactly calculated. So this is the overview of my talk. I'll start just introducing continuous time quantum walks to those of you who don't know them already. And then I'll tell you a little bit about the Maxcott problem. Eddie already introduced that in his talk, and the specific family of quantum walks we're going to study. And then I'll talk about two specific heuristics we can develop. First, what happens in these walks very soon after they start. And we'll see that we can build upon some nice ideas from the geometry of quantum evolutions to get some nice, simple expressions to understand that short time behavior. And then we're sort of more interested in what happens as the algorithm progresses. And in this long time behavior, we're able to use some ideas from statistical mechanics, such as thermalization, to develop a model there. And this helps us understand the performance of the algorithm. So a continuous time quantum walk is a sort of quantum version of a continuous time random walk, classical random walk. Probably the most familiar classical random walks are the discrete time, where you've got a walker traversing some graph, and each time step they toss a coin, and depending on the outcome of the coin, they wander in some particular direction on the graph. And you can form a continuous time version of this, where essentially now also the time at which they flip the coin is itself random. Okay, so the time that they finally move on is random, and it's determined by a differential equation. Okay, and this is a sort of differential equation which looks quite familiar, and we'll indeed see how familiar it is on the next slide. But just to point out what it means, so these PJs, this is just the probability that our walker has reached the jth vertex, and this L is a matrix called the graph Laplacian, which is basically just the adjacency matrix with some modifications on the diagonal to make this sort of behave a bit more nicely. But you can think of this as really the adjacency matrix. So the graph itself is sort of guiding the walker, and this is how this equation will evolve when we integrate it in time. So, of course, it's very familiar because it looks just like Schrödinger's equation, okay? And so a natural thing to do is to quantize this scenario just by taking this graph Laplacian as a Hamiltonian. It's a Hermitian operator, so you can do that in a straightforward way. And of course, Schrödinger's equation is now evolving. Schrödinger's equation has an almost identical form to the classical continuous time random walk. And the only difference there is this little I, but of course that has a major impact on the solutions of this equation and how the walk progresses. So meaning that continuous time quantum walks can behave rather differently to their classical counterparts. The Hamiltonian HD depends on the underlying graph, and in particular, when we have a hypercube structure, this becomes particularly simple. And in fact, it turns out that the adjacency matrix of the hypercube can just be written as a sum of Pauli X operators. Okay, so we have this very sort of simple form for the quantum walk on the hypercube. Now, this is a nice sort of toy to play with. It's a nice sort of simple evolution of a quantum system. But of course, just as in the classical world where random walks have been the basis of many algorithms, we would like to develop quantum algorithms. And this particular approach that I'm going to introduce now was introduced by Charles and Goldstone nearly 20 years ago. And they considered whether this kind of walk, continuous walk, could be used as a search algorithm. So this is a spatial search. It's looking for a particular marked node. And the way the node is marked is that a Hamiltonian exists of this form. It's just a projector onto the marked node, lowering its energy. And so you can form a joint Hamiltonian combining this HD, this driving term, which is causing the walker to walk on the graph, and this problem Hamiltonian here, which is marking out the solution. And Charles and Goldstone showed that this set of algorithms has some very interesting behavior, and in particular, there are certain scenarios you could kind of completely and exactly solve, such as on the hypercube. And here, you can see sort of the limiting behavior of this Hamiltonian when this gamma is very large or when this gamma is very small. You're either going to get the ground state of the Hamiltonian being this equal superposition state, which is just the ground state of HD, or it's going to be the ground state of HP, which is the solution term. So what they showed is as you vary gamma, you actually get this crossing, these sort of two regimes, one in which this superposition is the ground state and the other in which this marked state is the ground state. And you get this nice sort of transition, this nice crossing. And if you sit here in the middle, you'll just get an evolution between these two states. And you can use this as your quantum search algorithm. And indeed, it gives you a Grover-style square root speedup. So a very nice, simple example of the potential power of continuous time quantum walks. So we're going to study a slightly more complicated version of that, continuous time quantum walks for max cut. And max cut is a problem which Eddie already introduced to you. So we take our graph, we bipartition the vertices into two sets, and the weight of a cut is defined as just the number of edges between the two sets. And we want to find the max cut, the cut with the largest possible weight. Okay, so this is a nice, simple, all-purpose optimization problem. It's NP hard, so you can map many other problems into it in an efficient way. And it's sort of a nice, simple problem to convert into quantum form, because as Eddie already told you, the Ising Hamiltonian is a sort of a direct realization of max cut. So the Ising Hamiltonian, of course, will lower the energy when the two qubits. So if we just take one term of the Ising Hamiltonian, it will lower the energy when our two qubits have odd parity, and it will raise the energy if they have even parity. So this is giving an energy penalty corresponding to the cut. And so when we sum them all together, this gives us the value of the cut. And if we can find the ground state of this, we will find the max cut. So following the original work of Childs and Goldstone and this more recent development where continuous time quantum walks were studied for problems such as the spin glass problems, also discussed in Eddie's talk, we decided to focus on this slightly simpler picture and look at continuous time quantum walks for max cut. And all we do is we take the Childs-Goldstone picture and we choose for our problem Hamiltonian this Ising Hamiltonian here. Okay, and then the way the algorithm proceeds is that we start in this maximal in this superposition state, which is the ground state of HD, and we then just switch the Hamiltonian on. So this Hamiltonian here is a linear combination of HD and HP. And it's a constant Hamiltonian in time. We just switch it on, allow the system to evolve for a certain time, and then we measure in the computational basis. And we're hoping that this sampling in the computational basis will reveal a good solution to the max cut problem. Okay, and maybe not the optimal solution, but a sort of reasonably good solution that might be useful. So a natural question to ask is, in setting this up, there's really only two important parameters you would have to choose. One of them is the value of gamma, this sort of weighting factor in the linear combination in the Hamiltonian. And the other is the length of time you need to apply the Hamiltonian for. And you can, again, make a similar sort of analysis to Childs and Goldstone and realize that if gamma was set to 0, the system's never going to evolve because we're in the ground state of, we're in an eigenstate of the Hamiltonian. But if gamma is very high, then basically our Hamiltonian is just built out of Pauli Zs, and that commutes with the Pauli Zs we're going to measure on our qubits at the end of the computation. So that those observables are never going to evolve, and we'll be stuck in this uniform random measurements when we measure those at the end. So we need to find something in the middle, okay? And that's sort of part of the motivation for the techniques we've developed to find a good way to optimize that gamma. But before we look at that, just as a sort of a warm-up, a very simple thing we can do to study the behavior of these walks in the short time limit. And of course, if we take our time evolution operator and we just expand it to first order in t, well, this gives us an approximate evolution for the very sort of early times of the evolution. And we'll just have a very simple expression here. But you can see this is living in a two-dimensional subspace, right? We've got the superposition of the original plus state and then whatever state the Hamiltonian sends it to. And there is a geometrical property you can use which measures how much a trajectory deviates from a two-dimensional plane. This is something called torsion. Okay, so torsion really, it sort of measures the kind of the twistiness of an evolution. Here's an example. There's some nice sort of visualizations of curvature and torsion which you can find in Mathematica. And here's an example of an evolution with zero torsion. So this is a particle that's just moving on this elliptical trajectory. And because it's following an ellipse, you can see the entire trajectory is in a single plane, okay? And you can sort of see that this is sort of reflected by, we've got the normal vector here and the tangent vector here, and you see they're sort of all nicely sort of progressing around here. And so that's an example of a zero torsion evolution. But when you have a more sort of twisty evolution like this helix, you see you get a non-zero torsion. And I'm not going to go through the definition of the precise definition of torsion, but loosely speaking, it tells you sort of how rapidly the evolution is departing from a motion which could be described in a single two-dimensional plane. So it's basically telling you how quickly you leave this two-dimensional plane, which precisely is the scenario we're looking at in the short-term limit. And just a few years ago, there's a very nice paper which really takes all of these sort of geometric ideas and applies them directly to quantum evolution, so evolution under a constant Hamiltonian. And in particular, they derive this very simple expression for the torsion. So it's just an extremely simple expression just in terms of various moments of the energy of your quantum state. Okay, and these moments will be time invariant because, of course, this H commutes with itself, so it doesn't vary in time. And what they also showed in this paper was sort of the cutoff time, which the torsion tells you your evolution is likely to have departed from its original two-dimensional plane, is about the fourth root of the torsion. So we can use that limit. We can calculate the torsion for our max cut problem, and then we know how long our system will evolve before it leaves this very simple two-dimensional subspace. And because of the simplicity of the problem, the moments are very easy to calculate. And here's an example. So here's a moment. Here's the second moment. And you see it's just gamma squared times kappa 2, where kappa 2 is just the number of edges in the graph. It's a very, very simple calculation. If you do the third moment, now we're just taking this expectation value up to the third power, and now triangles come in. So our third moment depends both on gamma and also the number of edges and the number of triangles in the graph. And you can go higher, you can go to the fourth moment, and you get a more complicated expression. But the important thing here is it just depends on the number of edges and the number of triangles and now the number of squares. So these nice, simple things to derive. So this gives us a sort of a time limit on when our quantum walk is going to depart from this two-dimensional subspace. And just to give you some numerical illustrations of this, here's a graph that we generated. So most of the numerical experiments in my talk are going to be with 12-node graphs, random graphs which were generated with a probability for each edge being occupied of 2/3. So pretty complicated graphs. And here we see an example for a rather low gamma. And the orange line is the evolution, which would be sort of predicted by this two-dimensional this two-dimensional oscillation, which we can just derive from the expression a few slides back. And the purple line is the actual numerical integration of the Schrödinger equation. Okay, and you see it sort of works fairly well up to this t to the -1/4 limit. And here's another example where we increase this rather higher. And you see here the short time prediction is pretty bad, except for this very small region here, again, up to the t to the -1/4. So the torsion is kind of a cute sort of geometric tool we can use to study the short time behavior. But the main result of the paper is looking at the long time behavior. And here we turn to thermalization. And this is something that came up in Soon Won's talk yesterday. So the eigenstate thermalization hypothesis is sort of a very important idea in quantum statistical mechanics. It goes back to the 1990s. And it aims to answer the question, why can physicists use statistical mechanics in a world that is quantum? And in particular, why does statistical mechanics seem to work so well, even describing quantum systems, even isolated quantum systems? It's a hypothesis. It's not a theorem, even though it's been around for, 30 years. It has not been proved except for very special cases. But there's a huge amount of numerical evidence and even experimental evidence that it holds. So what does it tell us? I mean, essentially what it tells us is that generically, local observables in isolated quantum systems equilibrate. That means that if we've got some complicated quantum system with lots of interactions, probably lots of entanglement being generated as the system evolves in time. If if you just look at a small region of the system and look at the observables, they will typically thermalize towards some long time average value. So they're not going to do the thing which you might expect a coherent quantum evolution to do, which is sort of oscillate all over the place. They're going to tend to converge to these thermal values and then just have small thermal fluctuations from them. And this is such a broadly found phenomenon that people tend to study the exceptions. So there are very interesting physics in systems which don't have this behavior, and things such as many-body localizations are many-body localization is an embodiment of that. So locally, the system is behaving like a thermal state, and we're going to make the hypothesis that we can apply this to our continuous time quantum walk. Okay, so now the good thing is that in our quantum walk, both the driver and problem Hamiltonian are both local Hamiltonians. They're all sums of these little local terms. So if we're looking at the expectation values of these, they're going to be sums of lots of little expectation values of lots of little terms. So we'd expect that individually they will all thermalize and thermalize fairly rapidly. And to sort of see this, here's another numerical example from I think this is again an n equals 12 graph, just comparing the ground state probability to the expectation value of our problem Hamiltonian, okay? And you might think that the ground state probability would be a good measure of the performance of this quantum walk, right? Because isn't that what we want? We want to go to the ground state of HP. But you see it's a big mess. I mean, perhaps unsurprisingly, it's oscillating all over the place. Whereas if we look at the expectation value of HP, you see it falls quite quickly to this, something very close to this long time average. And then it just kind of oscillates around it with little thermal fluctuations, but stays close to it for most of its evolution. So this means that this expectation value is a good metric to use to measure walk performance. So in this long time limit, and really, you know, in this example, it wasn't very long. You know, after this very short time, we've already reached the long time limit. And the system is going to be in these thermal equilibrium. These observables are going to be in the thermal equilibrium states, and the quantum state will be well described by a Gibbs state. Okay, a Gibbs state of a certain temperature. So this is just the Gibbs state. If you're not familiar with it, this is the state we use to represent a quantum system in thermal contact with a heat bath, and it just represents the energy eigenstates being populated according to Boltzmann statistics. And the normalization factor here at the bottom, this is the partition function, which Eddie also mentioned. And the only free parameter here in the thermal state is this beta, which is just 1 over the temperature. You see, the thermal state is just defined by the temperature and the Hamiltonian. So we're going to assume that is our state. Once that we're going to assume that we can model our state by a thermal state and use it to estimate the local observables, which represent the sort of relevant quantities here that we want to study. And in particular, we want to know how can we find the best gamma to set up our quantum walk. So the nice thing about this model is it's so simple. To find the state we need to study, all we need to identify is the temperature. The temperature is the only free parameter in this picture. And, well, energy is conserved. So we know actually how to find beta. We just need to solve this equation. We just need to find the average energy of the state, calculate what the energy was of our initial state. It's just equal to minus n with this very simple Hamiltonian. And this fixes beta. So there are no free parameters in this model at all. If you give me the quantum walk, I will give you the thermal state, which is going to describe its long-term behavior. And so here's an example of it in action. Again, this is another n equals 12 random graph. You see, again, we have this sort of plummeting down of our of this expectation value of HP. That's good. That's the system sort of moving to a more optimal configuration. And then Once it sort of hits the prediction from the Gibbs state, we have this kind of thermal fluctuations around it. And this line here, this is not a fit. This is the prediction from the equation on the previous slide. So the model, and we tested it on more than just that one single example. The model appears very effective, but of course it looks difficult to apply because this is an exponentially big matrix. So how on earth could we do this for a problem of interest with a large graph and a large quantum state? Well, we turn again to statistical mechanics and to the partition function. So the partition function plays this really central role in statistical mechanics. It's used a little bit like a density matrix, if you like. From the partition function, you can derive all of the various thermodynamic properties of your system, like the energy and the free energies and the entropy. And if you know Z, you sort of know everything. And in particular, the mean energy can be computed from this very simple equation. So what we're going to do is we are going to build a simple model of our simple model thermal state by just taking a continuum limit. This is what happens in the thermodynamic limit anyway. What tends to happen is that the spectrum converges to a continuum, and we're just going to assume that that happens. And when we go from a discrete set of energies to a continuous set, our partition function is then defined by this integral. And the most important thing, the thing which really defines our integral, is this G of E, and that's the density of states. So we can build a model of the partition function by just specifying a density of states. So as a simple first attempt, let's just assume this is Gaussian. This is sort of the first thing you might try. And again, this is not any Gaussian. We're not going to do any fitting here. We're going to work out what the mean and variance should be of this Gaussian. And they are just going to be the mean and variance of the spectrum of our Hamiltonian. So that means we're just taking the trace of H and the trace of H squared. And again, these are quantities that are very easy to calculate. And again, they depend on these simple geometric features of the graph, like the number of edges. And you see you get a fairly good match. It's okay. So this is again one particular example, and this is the distribution of the energy eigenvalues of this Hamiltonian. And you see it's kind of Gaussian-ish, but it's a bit skewed. Okay, so the Gaussian isn't quite working. But so what we can do is we can take our Gaussian and we can skew it, and it turns out that there's a family of functions called the exponentially modified Gaussian, which are precisely that. They're a kind of a skewed Gaussian. And they're defined by 3 parameters, which essentially are the first 3 moments of the distribution. So what we can do, we can calculate our first 3 moments of our Hamiltonian. Again, they have these nice simple expressions. And we can then fit that to this exponentially modified Gaussian. And again, we've got a nice model for the density of states. Again, there are no free parameters. This was all obtained from the moments of the spectrum. And you see the match is pretty good. And we were quite happy with this match. And we didn't feel the need to go to higher moments. So the nice thing is now we've got this very simple model of the partition function. We can calculate all sorts of properties of the system, such as its temperature. And we find for both the simple Gaussian model and also this exponentially modified model, these are things which we can calculate analytically. And when you put the numbers in, you find these betas are rather low. In general, they're less than 1, which you can sort of easily see here. And that means the temperature is high. So that means the continuous time quantum walks from max cut are hot, which was the title of our paper. And even better, we can get an analytic form for this long time average for our problem Hamiltonian expectation value. And this is a kind of a truly remarkably beautiful expression. You can show that this value can be sort of obtained from the partition function in a very sort of similar way to, if you look in your statistical mechanics textbooks and look how you obtain free energies, etc., we can obtain this value for HP. And so this allows us to make predictions about what the optimal gamma should be. So here's an example with this dark blue line being the exact numerical calculation of this value for different values of gamma. And this is the prediction of our Gaussian model. You see, it gets it quite well. It's sort of a reasonable approximation, but it's not great. And the exponentially modified Gaussian gets a rather better prediction. And actually, it's pretty good in general. So here is some numerical data from 100 random graph instances of varying numbers of nodes, and the difference is pretty small. So the purple line here is the mean, and then this box, this is the interquartile range, meaning that sort of half of the statistics are in the box, and then the rest are sort of these long tails here. But you see most of the probability is here quite close to 0, meaning that this prediction is working at least for these examples. And also we can calculate what h bar p is going to be. So we know how well our algorithm is going to perform. And here we find, again, sort of a fairly tight range of values with this approximation ratio of about a half, meaning that, so the optimal value here is a negative number. So our estimate is sort of half of that negative number. And it seems to be sort of rather constant as we vary the number of qubits, meaning this is getting sort of reasonably good estimates for the optimal state, but fairly far from the exact ground state energy. And maybe this is to be expected from such a simple algorithm. So to summarize, we have developed these heuristic approaches for studying continuous time quantum walks based on some ideas from geometry and also from statistical mechanics. They allow us to make analytic predictions of the behavior of a given quantum walk, choosing the optimal value of gamma, and also predicting how well the final approximation ratio is going to be of the algorithm. And the nice thing is that in this max cut case, the values of these depend only on features of the max cut graph, which is rather nice. Now, we could certainly generalize these methods further. We haven't done it yet. It would be quite interesting to apply them to more general spin glasses, such as the walks studied in this paper by Adam Callison, which showed for certain cases some very promising performance. Or more generally, these ideas, you could use them in any scenario where you've got a constant Hamiltonian, such as quantum simulations. Sort of also motivated by Eddie's talk earlier, I think it would be very interesting to study what happens when we change the initial state. And maybe we'd also see some anomalous behavior if we preloaded this with a classical approximate solution. Maybe we'd find in that case the eigenstate thermalization hypothesis doesn't hold. It would be interesting to explore that. Certainly you can consider extending these techniques to study QAA and quantum annealing. We sort of make some baby steps towards that in our paper, where we generalize this to multi-stage quantum walks where the gamma is varied during the algorithm. And it's interesting to think whether these simple thermal models have direct implications for the presence or otherwise of any quantum speed up in these simple walks. There was a comment of yesterday, I think, from Jens Eisert, talking about whether, if you have a thermal model for a quantum algorithm, does that mean that there won't be any speed up? Well, not necessarily, because our thermal model is giving us some estimate of the performance of the algorithm, the expectation value of HP, but it doesn't actually tell us what the solution is. We can't use it to sample from the solution states. For that, we have to actually run the algorithm on the quantum computer. But maybe there's a way of sort of constructing a sampling algorithm using these thermal properties. And yeah, it'd be interesting to find where the eigenstate thermalization hypothesis breaks down. So can we find continuous time quantum walks where this thermalization does not occur? So thanks very much for listening, and this is where you'll find our paper. Thank you.
Thank you very much, Dan, for this very nice talk. Are there questions? Yes.
Maybe I didn't understand something, but how does your algorithm distinguish between maximizing h and minimizing h? Like if I substitute h to minus h, doesn't the same exact thing happen?
That's a good question. So, I mean, so there is a lot of symmetry in this problem. How do we? Why is it cooling down and not heating up? I mean, I think it's. I mean, it's not completely. I mean, I guess there's a sort of conservation of energy at play here, and the energy is sort of sloshing backwards and forwards between sort of being near a ground state of this and being near a ground state of this. And I guess that's what makes the distinction between the low temperature solution here and the high temperature solution. Does that answer your question?
So it's like the relative sign between these two terms is.
So yes, I mean you could just flip the sign of this, and yes,
okay,
and that would do what you're suggesting.
How should we understand this conclusion that the continuous time quantum walk is hot? Like, I mean, what does this mean? Like,
well, I think it's telling us something about the performance, right? I mean, you'd ideally want to have quite a low temperature solution, because the sort of the lower the temperature, the lower this this HP is, and the sort of better your final output would be. So in some sense, it's a bit of a negative conclusion to the paper that we're not seeing very low temperature states here when it's thermalizing.
This is naive and it doesn't work, but like, is it possible to, kind of repeat it multiple times, and then, if you have beta sort of non-trivially like low, then you get to a sort of lower energy state, then maybe you repeat again and you get to an even lower energy state. So you're sort of effectively kind of projecting.
Well, yes, I mean, you could think, I mean, something that's similar to that is if you sort of ramp up the value of gamma in time. And this is like, here you see, this is sort of, I think, what you were describing. Each time you ramp it up, we find the system thermalizes very quickly, and we're reaching a sort of a better solution. And you can sort of see each time this thermalization is occurring very quickly. So you actually, the time steps could be rather small, and this would still work. And yeah, this improves significantly on the quantum walk with a time invariant gamma.
More questions?
This plot, I guess, raises the question of whether there's ever a reason to do the continuous time walk rather than just annealing, as many people advocate. And the second thing I wanted to ask was, did you look at the integrable case where ETH nominally breaks down if you just do it on a cycle? I mean, that model's integrable, so it shouldn't be thermalizing.
Yeah, we haven't looked at that, but yes, that would be very interesting to see. And yeah, in that case, you wouldn't expect thermalization. I mean, as far as quantum annealing goes, I mean, these methods don't work very well for quantum annealing. I mean, this is kind of in the limit of lots of little lots of. I mean, this is essentially the same Hamiltonian. This is the same Hamiltonian as quantum annealing, right? And if we just sort of varied this continuously, in the limit, you would have quantum annealing. And you see, our model doesn't work very well in that limit, because then the parameter will be changing too quickly for the thermalization to occur. So it's a little bit ironic, right? In quantum annealing, you're essentially adiabatically staying close to the ground state the whole time, but in our model, the thermalization wouldn't occur quick enough. So It doesn't quite work for quantum annealing as it stands, but it'd be interesting to see if it could be developed for that.
Further questions at this stage? Let's thank Ben again.
Thanks, Eric.
And all other speakers of today. And then I look forward to seeing you all tomorrow at 9:30 for the day starting on quantum advantage, new applications and approaches, and with Scott Aronson kicking off the day.